Alright, so we have some more alkyne synthesis practice problems. So the first one is provide the structures of the expected major organic products from the following reaction. So what reaction do we have? Well, we have HBr and Rho. HBr are reagents that are halogenation. So we know we're going to add a bromine to the molecule, and Rho is hydrogen peroxide, and that tells us we're going to add that bromine in the anti-Makovnikov position. So when we look at this molecule right here, starting with the molecule, we can see we have a triple bond. So when we do halogenation, we're going to reduce that triple bond to a double bond. So let's draw out the molecule. We got carbon 1, carbon 2, carbon 3, carbon 4, and then 2 methyl groups off of carbon 4. So when we go over here, we have carbon 1, carbon 2, carbon 3, carbon 4, right? 1, 2, 3, 4, and then we have 2 methyl groups off of carbon 4, right? So we add another methyl group. Now, if this is carbon 4, right, this is 4, this is 1, and there's a triple bond that we know is going to get reduced to a double bond between carbons 1 and carbons 2. So we now have the double bond in there. Now, HBr is going to react and add in the anti-Makovnikov position because of Rho, right? Because of hydrogen peroxide. So we know the Br is going to be attached to carbon 1 in the anti-Makovnikov position. And this is your major product. Okay, so for the second one, provide the structures of the expected major organic product from the following reaction, right? So we have another triple bond right here. And we have diazamylborane in hydrogen peroxide and NaOH, right? So we know this is going to be hydroboration. And diazamylborane is also written as 9BBN. So if you see 9BBN, it's diazamylborane, and it's a hydroboration reaction, right? So again, we know we're going to reduce the triple bond down to a double bond, and the hydrogen peroxide also means it's going to add anti-Makovnikov. So let's draw out this molecule, right? So we have carbon 1, carbon 2, and then we have 2 methyl groups off of carbon 2, and we have carbon 3, carbon 4, and carbon 5 right here, right? So we come back over here, and we have carbon 1, carbon 2, carbon 3, carbon 4, right? And carbon 5, right? So 1, 2, 3, 3, 4, and 5. Now we know off of carbon 3 there's going to be 2 methyl groups. So we'll draw these in. And we know between carbons 1 and 2, that triple bond will be reduced back down to a double bond. And we also know an oxygen will be added in hydroboration. So this is the final product. Number 3, provide the structures of the expected major organic products from the following reaction. So we have, again, a triple bond, and we have ozonolysis, right? Because we have O3 and H2O, so we know ozonolysis is going to split this triple bond right down the middle. So we know we're going to get two molecules. I find the easiest way to do ozonolysis problems is to draw both halves of the molecule and then add the oxygen onto it. So we know we're going to have basically an aldehyde, and then we're going to have a carbon here, carbon here, carbon here, and two methyl groups off of that. So what that's going to look like is we're going to have the carbon, we're going to have carbon 1, carbon 2, and then a methyl group and a methyl group on one side, right? And then plus, we just have a carbon right there. And then we have to add the oxygen on, right? So we know the two hydrogens. There are two hydrogens right here. They're going to get oxidized. Well, there are actually three hydrogens. They're going to get oxidized, right? Because carbon forms 4 bonds, so there's 3, but one of them is going to get kicked off. And we're going to form a double bond. So we're going to have the oxygen with a double bond, and then an OH group for the other carbon. And then we're going to have the same thing. We're going to have a double bond with an oxygen, and we're going to have an OH group. Okay. 3. Provide the structures of the expected major organic product from the following reaction sequence, right? So we have a terminal alkene, and we have an alkylation reaction to add this carbon chain onto the end of that terminal alkene. And then we have Lindlar's catalyst, which reduces that triple bond down to a double bond. So we're basically going to have an A and a B product, right? So our A product, we'll draw out our starting material. And then we're going to add this carbon chain onto the end of the triple bond, right? So that Br will get pushed off, and we're going to be left with that very poorly drawn carbon chain. Next, we have Lindlar's catalyst. So Lindlar's catalyst is going to reduce that triple bond down to a double bond, and it will reduce it down to a cis alkene. So we're going to have this. Right? Because this is cis, right? That's cis configuration. To be clear, this is wrong. This is trans. That is not a product of this reaction. It has to be in the cis configuration because Lindlar's catalyst pushes to that configuration. It does not do the trans configuration. So there is your major product.